Assalamu alaikum. In today's lab session, we'll be dealing with how to handle audio codec on DSK6713. The purpose of today's lab will be to manage the codec and to enable analog input and analog output from our DSK6713. The main aim of today's lab is to understand how our DSP processor will be able to handle data coming from analog input. If you remember from our initial introduction to DSK6713, we had 4 analog lines. 2 of these were mic in and line in. These will be used for carrying data inwards, and 2 of them are line out and headphone, which will be utilized for carrying data outwards. In our case, these 4 analog lines are connected to our DSP board, rather to our DSP chip, through an audio codec by the name of AIC23. This codec is highly configurable and is optimized for audio processing applications. This codec is connected to a 12 MHz system clock. Furthermore, it is a highly configurable and tunable codec. That means that there are a number of tunable factors such as the sampling rate, which can be chosen from 8 kHz to 96 kHz. Similarly, it supports various quantization levels from 16 bits to 32 bits. Now, if you want our DSP processor to work on an analog input, this can easily be managed through this AIC23 codec. The AIC23 codec will provide the quantized data to our signal processing algorithm running on DSPKit through MCBSP, which is a multi-channel which is a multi-channel buffered serial port. Now the communication of AIC23 with the DSP processor is either carried out through interrupt signals, or it can either be done through pooling. For today's case, we will be dealing with pooling as a mechanism for communicating data between AIC23 and our DSP processor. Before we jump into the details of how the code works or what are the main functions for running codec on DSP kit, we first need to understand the peripherals that codec deals with and how the configuration or the different tunable parameters can be changed. The very first thing that comes to mind is the input lines and the output line selection. As already stated, we have 2 input lines to choose from. Similarly, we have 2 output lines to choose from. We are given this possibility that this codec can handle one of the input lines and the output can be provided on one of the output lines. This management of configuration of choosing which of the lines will be utilized, this is done through some certain amount of control registers. In essence, AIC23 has 10 control registers. Every register is 16-bit byte. Certain bits of every register play an important role in selection or configuring this AIC23. For example, let's just talk about this number 8. Number 8 deals with sample rate. So if I need to change the sampling rate of my AIC23, I might need to toggle some of the bits of register number 8. Similarly, there are 9 other registers that will be dealing with different kind of information that AIC23 can configure. In order to handle the working of AIC23 codec, be that the reading, writing, or the configuration of 10 control registers which we talked about in the previous slide, we need to have some form of an API support or API calls available to us. This can easily be managed by the support given to us from DSK6713 BSL library. In that library, we are provided with a header file, namely dsk6713_aic23.h, which contains definitions for a number of different API calls. These API calls may include read, write, and configuration of the 10 control registers. Here we'll be talking about 4 to 5 of the main functionalities that are often used whenever we are going to deal with AIC23 codec. I'll simply name them and then we'll discuss them one by one in the later slides. The first command is AIC23 open codec. This command is utilized. This command is used to open a codec with regard to a certain configuration parameters. Second, we have the close codec. Once we are done with the processing or once we are done with the codec, we need to close the codec for further subsequent operations. The third command deals with configuration. This command is used to manage the 10 control registers, and this command actually provides us the facility that we can overwrite different configuration bits of one or all of the 10 configuration registers. Finally, the last two commands are read and write command, subsequently allowing us to read data from the AIC23 codec, or it will allow us to write data to the output line of DSPKit through AIC23 codec. Now, coming to the very first command, that is open codec. This command requires at least two of the headers to work correctly. Whenever we are going to work with AIC23, we need to add these two headers, that are DSK6113 and DSK6113 underscore AIC23. Because both of these commands, both of these header files contain the functionality that will be required while dealing with AIC23. The commands other than open codec which will be requiring to open a codec are DSK6113 underscore AIC23 underscore codec handle. This will be defining a codec handler through which we will be operating upon the AIC23. Meaning all the subsequent commands of AIC23 will not be handling the codec directly, rather they will be handling codec through this codec handle and the name provided here. Second command that is going to be utilized is the configuration. This configuration essentially defines a variable by the name of config, which will be able to save 10 16-bit values. These 10 16-bit values will correspond to 10 control registers for our AIC23. Finally, once we have declared a codec handle, once we have set the configuration, we can easily open our codec. Now the command and the associated parameters for open codec are: open codec, the first parameter is int id and the second parameter is and config. We are essentially passing the address for this config variable, which saves the 10 control register values. In our case, this ID will be 0 because we are working for DSK6113. This is always going to be the case when you start off and you start working on DSK6113. As a reminder, this config essentially contains the codec register values. How these are generated, we will see in later on slides. Before we cover the overall example for open codec, let's cover a very basic example showing snippets of code that will be required to open and correctly close a codec. The very first step in opening codec will be the definition of config registers. And this can be done by first utilizing AIC23 underscore config command and declaring a variable. This variable name can be user defined. This is a user defined name, so it does not necessarily mean that we need to write config here. Any name can be utilized here. Then here we have saved 10 values, and you can see that every value is mentioned in hexadecimal and every value is of 16 bits. For our ease, we can see that the first value corresponds to to control register number 1, which deals with left input volume, second deals with right input volume, and so on. So these 10 values will be directly corresponding to the 10 control registers of our AIC23. Interestingly, we are already aware of these values. These values the default values can be gotten from the header file. So we do not need to remember all of these values. But we need to understand how these values are set. So we'll be covering that in a bit. Once we have defined the config values, the next step is going to be opening the codec with regard to these config values. This can be managed by first defining the codec handler by the use of codec handle command. Codec handle space hcodec. Again, this can be a user defined name. Once we are done with the definition, we simply need to open the codec. Now, opening codec was easy. First, we need to give in the ID, which defined the type of codec we are using. In our case, this will be set to 0. The second was the address of config. We have passed it through and config. The returning value from this command is actually the codec handler. This codec handler now will open the codec with regard to the configuration mentioned in config. Now that we have successfully opened the codec, we can proceed with all the signal processing that is required either on the acquired data from AEC23 or from self-generated data. Once the signal processing is done and relevant read and write operations from the codec are taken care of, we need to close the codec using close codec command, and this time around we'll only be passing the codec handler. So this is a snippet, and this setting is going to be utilized in all of the examples wherever we are going to deal with AAC23. The majority of the change that can occur is these values that I've mentioned here, because these are the default values. They may be changed from time to time. Whenever we are going to deal with a certain configuration, we might need to update these values. In the last slide and a slide previous to that, I have mentioned time and again that we might be requiring to change the values of control registers to suit our needs. In order to understand what those 16 bits correspond to and how and what effect changing one or multiple bits will have on the performance or on the working of AAC23, we need to take an example. For this matter, I have chosen register number 5 from the control registers, that is audio path control register. This is one of the most frequently changed control registers, so I'll be talking about this. This register essentially deals with the choice between the input lines available to us. That means that we might be selecting microphone as an input line, or we might be selecting line in as an input line. A microphone, of course, will be dealing with the audio signals, whereas line in can get data from anywhere. And it can get data from an analog sensor. It can get data from a function generator, where we have generated our custom sinusoidal or custom signal that we require for processing. So already discussed is that every control register is of 16 bits. It is not necessary that all the 16 bits are being utilized by every control register for setting or for configuring their values. In our example, only 9 bits of these 16 control bits are being used for setting different kind of parameters. Let's talk about every bit one by one and see what effect every bit has and how changing them will help us in configuring AAC23. Starting with the bit number 0, which is D0. D0 deals with microphone boost. If this is left to 0, it means no additional boost will be added to the signal. If it is set to 1, boost of 20 dB will be added to the signal. It means that D0 is not a very essential bit for us. It can be set to 0, it can be set to 1, it won't really matter. The only difference that we'll get is the amplification factor. Bit number 2, D1, it deals with microphone mute. This is an important bit because whenever we are going to deal with the microphone, we do not want the microphone to be mute. So in order to unmute the microphone, we need to set D1 to 0. Whereas if we want to mute the microphone, this bit has to be set to 1. Unfortunately, the default settings are in such manner that microphone has been set to mute by default. So if we are going to utilize microphone, we need to set this bit to 0. The third bit deals with in select. That is very obvious that it will either be choosing the line in or it will be choosing the microphone as the input carrying line. So if we are going to deal with microphone, we need to set this in select to 1. Whenever in select is set to 1, it essentially means D1 automatically should be set to 0. Because if we do not care, if we do not take care of selecting both D2 and D3, D2 and D1 in accordance to the settings mentioned here, we even though we might have set the microphone as our input line, but we might not be getting any signal because the microphone might be muted from D1. So till now, if we are going to utilize microphone, I need to set the bits in this manner: D2 as 1, D1 as 0, and D0 can either be 0 or 1. It does not really matter. Coming to the fourth bit, D3. D3 essentially tells us to bypass the ADC or not. Whenever we are going to use AAC23, this bit has to be set to 0. So if I'm going to utilize the microphone, now the combination of the last 4 bits becomes 0, 1, 0, 0 or 0, 1, 0, 1. Finally, the fifth bit D4 deals with DAC. That do we need to select? Do we need to enable the output that is digital to analog converter as well? So it is by default set to 1. So we are not really concerned. We can set it to. We can let it be set to 1 unless we are planning not to use the DAC. In that case, we can set this to 0. The remaining 4 bits are used in a combination. These 4 bits are used to add a side tone to the signal. I won't be talking about the details because it can be easily read from this table that what combination will add what kind of a side tone to the signal. All we need to consider is the last option, that is if we set the bit number 6 that corresponds to STE to 0, no side tone will be added. So in our examples or in our demonstration for today, we will be setting this STE bit to 0 so that no side tone is added, plus DAC will be set to 1 and bypass will be set to 0. In short, the final configuration values for register number 5 against audio path control register will be 000, tetra 0, 1, 0, 1, 0, 0, which essentially corresponds to 1 5 or 1 4 depending upon either you add boost to the microphone or not. So I hope this clarifies how different control registers will enable us control over functionality of AAC23. In similar fashion, we can change other control registers to suit our needs. Previously, we saw that the configuration of the AAC23 can be handled through different bits of the control registers. Interestingly, that is not the only way. There exists a certain amount of commands that can also change relevant bits. For example, here we have a set frequency, a command that corresponds to set frequency. This command can be utilized to change the sampling rate at which the AAC23 will be working. The command takes 2 parameters as input: the H codec, which is the codec handler, and frequency at which we need to sample or at which we need AAC23 to sample the input data. By default, if we do not make use of this command, the default sampling rate is set to 48 kilohertz. The frequencies at which we can sample our signal is already defined in the header file. The frequencies that we can choose from are 8, 16, 24, 32, 44, 48 and 96 kilohertz. So if we want to utilize a certain f of s from these available options, all we need to do is write H codec, the codec handler, and in the second parameter we need to write one of these options, which will be corresponding to one of these frequencies mentioned in the right hand side of the table. So now we have understood how configuration can be made. There are two options to it. Either you go about changing the different bits in the control registers, or in some cases we have available functions, available API calls, which will be directly helping us in changing the values of control registers. Having understood the working of Open Codec and the associated configuration registers, it is time to dive into the last two commands, namely the read and write commands. The syntax for read command is very easy to understand. The first part of the command remains same for all the AAC23 commands, that is DSK6713 underscore AAC23 underscore. Now we have read as our command. The read command contains two parameters. The first is essentially the codec handler, and that is going to be part of all the commands, the H codec. Second parameter is the address of the variable, a 32-bit variable, which will going to contain the returning sample value. It means that this command will not essentially return a sample value, rather the sample value to be returned will be directly passed through the parameter. I've already talked about this. The first parameter is H codec, the second parameter is the value, or rather the pointer to 32-bit variable to get the data. The return values for this command are actually a little different. This command either returns true or false. True will mean that a successful read has completed, and a false of course will mean that we are currently in the process of reading. And if you're utilizing pooling for reading and writing process, it means that our code should be stuck at this point until a subsequent read or a successful read has taken place. The read command has a couple of important aspects associated to it. Whenever we read a certain sample from the input line, that certain sample essentially contains information about both the left channel and the right channel. It means that if we have chosen a quantization level as 16 and we have read a sample of 32 bits, essentially that 32 bit will now contain 16 bits of left channel and 16 bits of right channel. The left channel information is usually stored in the higher word, that is the most significant 16 bits, whereas the right channel information is saved in the least significant 16 bits. It is emphasized that we need to work upon both channels separately. Whenever we are going about signal processing on the left and right channel, it's necessary that both are operated upon individually. In order to do that, we need to somehow mask and shift the relevant bits out of this sample, rather out of this 32-bit sample. The syntax here is quite easy to understand. In order to get the left channel bits, we need to nullify the effect of least significant bits. It can be done by masking. This code written here specifies masking in C. Here we have masked the least significant 16 bits by 0. Once this constant and this sample are AND together, the least significant bits are turned to 0. Once that's done, we'll simply shift this answer by 16, so that the most significant bits are now placed in the lower 16 half of the answer. Similarly, for right channel, we need to nullify the effect of most significant bits. This can be done by reversing the order of the masking bits. Now the most significant 16 bits for the mask are set to 0, whereas the least significant 16 bits of the mask are set to all ones. Once we AND these two, the resultant will now contain only the relevant information in the least significant, or in case of left channel, in the most significant information will be available. Finally, we also need to consider that the definition of left channel and right channel be in such manner that they make use of only 16 bits each. This can be managed by the conversion for left channel and right channel as short int instead of utilizing int32. Finally, it's time to close this discussion by discussing the write command. The write command works in similar fashion as read. The only difference here for this command is the syntax. Initially, the write instead of read will be placed in the syntax. Secondly, the parameter list is the same. The first shares the H codec. The second one, now instead of sending the address of the pointer for the variable, directly communicates the data that has to be written. Finally, in similar fashion to read, the write command returns true or false as the returning variable. True will inform us that data has been written successfully, whereas false will identify that the data port is busy, meaning that we are still in the process of writing the data, and we need to stall all the other operations until this data has been successfully written. In order to understand how read and write commands are going to work, we shall consider a very basic example. This example will be making use of the returning values of true and false from the subsequent read and write commands, so that the overall system can be stalled until a relevant read or a relevant write takes place. Here we'll be dealing with the write command only. In order to write data to the AAC23 codec, we have made use of a 32-bit variable which has been pre-allocated a certain amount of data that we need to write to AAC23. Now in this the first command or the first instruction is easy to understand, but the second instruction is a little tricky. The second instruction is essentially not only writing the data to the AAC23 using the write command where H codec and data have been passed, but this whole command has been placed in the terminating condition of the while loop, and essentially this while loop is empty, because here we can see that the the while loop has the terminating semicolon, which means that this while loop is essentially doing nothing but waiting for this terminating condition to occur. And this, if you look at this terminating condition, it's telling this while loop that until this command returns, the right command returns 1, we will be stuck at the while command. It means that this while loop will keep on working until a successive write has taken place. So essentially it creates a loop until the port is ready to transmit the data. So this syntax essentially can be used for read as well. Both these syntax will be stalling the system at their particular location until relevant read or a relevant write takes place. Having understood how an AIC codec can be utilized to communicate between DSPKit and the analog input and output in real-time fashion, we are now ready to perform real-time operations using a DSP processor. There is a catch while processing real-time signals on DSP processor or on any processor for that matter. That catch leads us to a very important observation. That observation is the available time between two successive sample reads. That time available to us between two successive sample reads essentially defines the number of operations that can be performed before a correct sample can be read. If somehow we have utilized a very complicated algorithm which exceeds the time duration between the two samples, the overall impact will be incorrect. That means the algorithm might be working in MATLAB. You might have tested your algorithm in MATLAB or any other language, and it might have given you correct answers. But when you translated that algorithm for DSPKit, that algorithm will fail to give you the same answers. That failure can occur due to the loss of input samples. That can occur due to any other reason, given that the algorithm does not adhere to the time that is available between two successive sample reads. So that the important observation here is that we need to understand the number of operations, the number of cycles, or the time that is available to us between two successive reads of input samples. Now, these successive reads are defined or controlled by two parameters, namely the FFS, the sampling rate selected for our audio codec, and the clock frequency of DSK. First, I'll be discussing the clock frequency of DSK, and then taking an example of FFS, we'll learn how many cycles, how many operations do we have available between two successive sample reads. The clock frequency for our DSK 6713 is 225 MHz. It might seem a very low clock rate in comparison to your general purpose processor, but the interesting thing is that the DSP processor can allow us to run 8 parallel instructions in a single cycle. It means that even though we are working at 225 megahertz, but if we employ maximum parallelism, the overall instructions per second come out to be 1800 million instructions per second. Moreover, the time between two successive sample reads comes out to be 4.44 nanoseconds. Now this time is of importance for us because let's consider an FFS of 44.1 kilohertz. If we consider an FFS of 44.1 kilohertz, it leads us to a time of 22.68 microseconds between two samples. Now this time and this TC will enable us to calculate the number of operations or the number of cycles that are available between two successive sample reads. This can be calculated by taking the ratio of T and TC. The ratio returns 5108, which is the amount of cycles available at our disposal. As already stated earlier, that in every clock cycle we have the opportunity to run 8 parallel instructions. These are the upmost possibility. It is not necessary that at all times we might be executing 8 parallel instructions, but we are going to go with the upper limit here. So if we have 5108 cycles available at our disposal, it means that 5108 into 8 number of instructions can be executed between two successive sample reads if f of s has been set to 44.1 kilohertz. So this essentially controls the algorithm, or this essentially controls uh, how complicated an algorithm can be implemented on a sample that has been read with f of s as 44.1 kilohertz. But interestingly, if we are making use of both left and right channel information of the sample that has been read, these number of instructions are halved, because each channel will be utilizing some form of instructions. So we can say that every channel will now be utilizing 20,000 every channel will now have 20,432 instructions that can be executed before the next sample has been read. The last word here will be that these are instructions we are talking about. This is not the line of code for C. These are the machine instructions, the eventually generated machine code from the compiler. These are those instructions that we are talking about. So these cannot be directly calculated. You might need further discussion or further instruction for DSK6113 to understand how and how many instructions are being utilized. Having understood the basics of AIC23, having understood how different configurations are made, having understood how read and write can take place, now we can easily move on towards the tasks that we need to perform for today. For today's lab, we have two different tasks to consider. The first task will deal with the generation of sine tone signal, which can be generated in similar fashion as last week. And once that sine tone has been generated, we'll try to hear that sine tone using AAC23 codec and our headphone. We'll loop that infinitely. We'll loop back that sinusoidal infinitely such that a continuous tone is heard on our headphone or on our line out. The second task will deal with real-time operations. That is, we'll try to initially loop back the audio being read from the input line, and the same audio will be tried to be looped out onto the headphones. In between, we can perform any kind of operation, be that a simple echo or simple filtering. That does not really matter, but because our lab is concerned with dealing, it's concerned with how we deal with AIC23 codec and how we can manipulate that to give us a real-time input data and real-time output data on the go.
Let us now move towards the implementation of both lab tasks on Code Composer Studio. The first lab task was aimed at generation of sine tone and hearing that sine tone using our headphones. In order to save time, I have already generated the project and all the relevant settings that are required to successfully run this project have taken place. Let's just review those settings. In order to review the settings, we need to right click the project, select properties. In this window, there are a few options that we need to change. Let's see if we have made all the relevant changes or not. First, we'll go about checking the changes that were required in the compiler option. Selecting compiler, and then we'll select include options. This include option tells us about the header files that are to be included in our project. We need to include the search path for all the chip support library header files and the board support library header files. We can see that both directories have been included in our project. The second change that we need to make in our compiler options is the definition of symbol, or the predefined symbol for that matter. Here we can see that a predefined symbol has already been defined by the name of chip_6713. These are the only two changes that are necessary, though there are other changes as well, but we are only going to deal with these two changes in the compiler options. Now coming to the linker options, linker setting is the one where we need to add the relevant library files. So in the linker option, we'll go to the file search path. Here we can see that we have already added the board support library and the chip support library in our project. After the addition of these two libraries, we also needed to add the runtime support library in our project. Let's just quickly select the general settings. In the general settings, the last option tells us about the runtime support library. Here we can see that RTS6700 has successfully been selected here. It means the main settings with regard to the library and the header files have already been completed. The last setting that had to be incorporated in our project was the addition of target configuration file. In the project repository, we can see that we have an XML file. This XML file represents the target configuration. Let's just double click this and see if the correct options have been selected or not. In the connection option, we can see that the relevant Spectrum Digital DSK onboard emulator has been selected, and for the board we have selected DSK6713. It means that current selection is correct, and our project is good to go. Let's just quickly dive into the code. In order to run the AAC23 codec, we needed to add the library files or the header file named DSK6113_AAC23. Apart from that, DSK6113.h has already been added. We may or may not add stdio.h. This can be used for input and output operations, though in our code we are not using this. Last header file that is required in our code, at least in this lab task, will be maths.h. We'll be using this library to generate a sine tone. Before jumping into the codec and the relevant commands for the codec, let's just quickly see how we have generated a sine tone. As per the last lab, we have successfully generated a sine tone of 10 Hz, sine of 2 pi into f. T has been stated here. The signal length here has been defined originally as 2000. We can see that the length has been defined as 2000. It means that sinusoidal with 2000 values has been generated and saved into a new register, a new array. After successful generation of sine tone, we need to output this sine tone or this generated signal onto the headphone signal. In order to do that, we need to configure our codec, and we need to open it, we need to write data to it, and once we have written data, we need to close it as well. So all these three options will be done one by one. In order to open a codec with regard to a certain configuration, we first need to define the config structure. This config structure is defined as AAC23 config. In this first example, we are not going to change any configuration, so because we only require to output the data on the headphone line. We are not getting data from the input line, so we'll be using the default configuration. This default configuration is added from the header file. Hovering over this default configuration, I can see the values it has saved. We can easily scroll through these values. So here we will have 10 different values corresponding each to the 10 control registers. Once we have assigned config with these initial default configuration values, we need to start declaring a codec handle. Here we can see that a codec handle has been defined by the name of hcodec. All the preceding commands for AAC23 will now be happening through hcodec. Once the codec handle has been defined, we initialize our board using DSK6713_init command. After the board has been initialized, we just need to open the codec in accordance to the configuration defined here. This was managed through the open codec command, which takes two parameters. The first one was the ID. The ID defines the type of DSK. In our case, the ID was set to 0. The second parameter was the configuration, which we have already defined, so we passed the config here, the config settings here. The resultant, the returning value from this open codec is essentially the codec handler, which we'll be using from here on. Next up is the code for the generation of sine tone. Once we have opened the codec in accordance with the settings here, we can now simply write this ANU data onto the output line one by one. We need to understand this, that the codec will be able to handle the data, but in a sample by sample manner. So the very first possibility that we can simply write another loop, for loop, which starts from 0 and goes to len. and one by one we can pick the ANU signal, and this ANU signal can be passed on to the right signal to the right command of audio codec. But doing that will only enable us to read or only enable us to hear the sound of 200 samples. The right approach for hearing a continuous tone will be to write an infinite loop where we start processing this data, and by processing we simply need to read the array one by one, and we need to continuously output the signal over the AIC output line. This can be easily managed by the use of an infinite loop. Here we have used a while one. In the while one, I have tried to read the 2000 samples of ANU one by one. In the first iteration, the 0th sample will be read, which has been multiplied with a gain. This is now a current sample. This sample will be output using the write command. The write command took two parameters. The first one was H codec, already defined earlier. The second one was the data that has to be output from this from our code. So we can simply pass this sample as parameter. Interestingly, as discussed earlier, this command has been placed as the terminating condition of this while loop, so that this statement stays intact until a single value of sample has been written over the analog output line. Now, by placing this for loop in this while one enables us that a continuous stream of output signal will be heard. Out of this while loop, even though we will not be getting out of this while loop, but out of this while loop we need to write the syntax for close codec. We can have a different type of settings. We can use dip switches to exit from this while loop, but for today that is not our aim. But we can add different type of logic here, which can enable us to exit from this while one loop. Let's see if this code has been correctly written. If this code is correct, we will be able to debug and hear a continuous stream of data using our headphones. A successful build shows that at least the code is correct. Now we just need to run the debug option. Once the debug window has settled, we can simply resume the code that has already been programmed on the DSP processor. We should understand this, that as soon as we press the debug button, the hexadecimal file, the out file, .out, specifically it's a .out file that has been generated against your project, which contains the machine code of your C code that we have already written here. That machine code has already been programmed to our DSP processor. But after the programming, it is now waiting for the instruction from this Code Composer Studio to start its execution. So as soon as I will press this resume button, our code will start running on our DSPKit. It means in our case, as soon as I press this button, I should start hearing an audio sound, rather a sine tone.
In order for you to hear the sound, I have set up the system in such a manner that the headphone has now been connected through an auxiliary cable to the speaker, so that as soon as I start playing my code on DSK6713, I'll hear a subsequent sound from the speaker.
As soon as I press the resume button, our code will start working on our DSP processor. That means that we should hear a sound, a sine tone sound from our speaker. As soon as the resume button has been pressed on the debug window, I start hearing a sound from my speaker. Now this sound corresponds to the sinusoidal signal that was generated in our code. Changing the frequency of our code will simply change how this sound is produced. Changing the gain of the system will only change the amount or the intensity of the sound being heard from the speaker. So this completes our task number 1, where we have successfully generated a sine tone, and we have heard that sine tone on the speaker using AIC23 codec. Moving towards the second lab task, where we need to design a code which will enable us to loop back our audio from the input line towards the headphone. Again, as per the last lab task, I have already completed the project. All the settings, all the relevant configurations have already been completed here, and the code has already been written. I'll quickly go through the code here as well. After adding the relevant header files, that is DSK6713 and AIC23.h, we need to start adding the relevant functionality for AIC23, which in our case starts off with the definition of config register, or the 10 configuration registers. We do not need to remember all of these values. These values can already be attained from the header file. In order to go into the detail of the header files, I just need to click this header file, which leads us to the content of the header file. Here I can browse. After scrolling down, I can get the default configuration for these 10 registers, which show us all the different values for every register. Not only do they show us the values that have already been set by default, but they also show us the meaning of each and every bit, and what status they have been set originally. Let's just quickly review the analog audio path control register that we studied in the slides as well. The default setting for this register is set to 0011, which corresponds to microphone boost being enabled, microphone mute being disabled, in select as line in, bypass as off. That means that we are going to be using audio codec. The DAC has been set to 1, which means digital to analog converter has been selected. Finally, STE side tone signal has been set to 0, that is no side tone will be added. If we use the same configuration, we will not be able to use the microphone as our input line. In order to change that, we need to make a couple of changes in this setup. Initially, the setting that I have utilized, in that I have not made use of boost signal, so this bit was turned to 0. Mic mute has to be disabled, that is correct. In select has to be changed from 0 to 1, so that instead of line in, now I can select microphone as my input line, so this will be turned to 0. Bypass will remain 0. Eventually it means that our setting will come out to be, I'll just write it here, our setting will turn out to be 0001 and 0100. This corresponds to the least significant 4 bits starting from D0 to D3. The next 4 contribute from D4 to D7. This binary can easily be converted to a hexadecimal, which is going to map, this is going to be mapped on 4, which is stated here, and the next 4 bits will be mapped to 1, which is also written here. So now the control register values for register number 4, that is register number 5 for analog audio path control register, is to be set at 0014 instead of the original values, which was set at 0011, which meant that line in was selected instead of microphone. In this manner, if we need to make further changes, that can easily be incorporated. We just need to go into the details of this header file, read the relevant register, read the relevant bits of that register, and make changes in accordance to what our needs are. Once we have declared this configuration, the next step becomes very easy. In the next step, we first define the audio codec in similar fashion as the last lab task. Once the audio codec handle has been defined, we initialize our board using DSK6713 init command. After that, we start the codec. The codec will be started using the open codec command, which took 2 parameters. The first one being the ID, which was set to 0. Second parameter being the config register values. Now you'll see that the config values are the ones which are the reflected values here are the ones which are defined here. So it means that now once the codec has been opened, it will now use microphone as the input line without any boost signal. Once we have successfully opened the codec, we may or may not set frequency. As we did not make use of this command in the previous example, let's just see how set frequency works. The command structure is similar to all the other AAC23 commands, and that is DSK6113 underscore AAC23 underscore set frequency. It takes two parameters, first one being the codec handler, the second one being the frequency at which we need to set our AAC23, which in this example has been set to 8 kHz. Once frequency has been set, the next step is very easy to understand. In the next step, we need to read a sample of data from the analog input line. The same input, the sample that has been read, can either be set as output towards the headphone. If we want to perform some operation in between, it can easily be performed. If we run these two commands one by one, that is a single instance of read and a single instance of write will only enable us to read a single sample from the input line, and only a single sample will be written at the output line. This is because unlike MATLAB or unlike other programming languages, we are now dealing with a real-time system and a codec which will only be providing us a single sample at every iteration of that command. That means at every execution of read, we will only be getting a single sample of the input data, though that sample itself may be contributing towards the left channel and right channel as discussed in the slides as well. So in order to read a continuous stream of data, we need to put these two commands in a while one loop so that a continuous stream of input data and output data can be heard. Initially we'll simply read the data. In order to read the data, we first pass on the codec handler. In the second, we pass on the variable in which we need to save the 32-bit data that is being read from AAC23, or that in particular that is being read from the input line, that is microphone. This whole command in similar fashion as write has been placed within a while loop, rather within the terminating condition of the while loop, so that we will be stuck at this command until a new sample has been read successfully. Once we have read the sample, we can do any kind of processing. In our case, I have simply separated the left and right channels. The separation of left and right channel has already been discussed. The left channel, the information of the left channel is placed in the upper half of the sample being read. So in order to retrieve that information, I first mask the least significant bits of in using this mask. The contribution of the least significant bit is set to 0. In the second step, I simply shift the resultant answer by 16 so that only 16 relevant bits of the most significant answer are saved. This answer is saved into outl, and if we go about the declaration of in and outl, we can see that in was set to a 32-bit integer, whereas outl and out are set as 16-bit integers. This was one of the points that was emphasized whenever we were to deal with AIC23 codecs. In similar fashion as outl, we can extract the right channel information, which is in the least significant 16 bits of in. So the masking becomes different. This time around, the higher portion of in has to be set to 0. So the while AND operation, the mask has 16 zeros in the higher portion and 16 ones in the lower portion, which leaves us with only 16 relevant bits of the contribution of least significant 16 bits is left. Once we have successfully extracted both the channel information from the input sample, we can perform any kind of signal processing here on. That signal processing, for example, can be a low pass filter, it can be a Fourier transform, it can be any kind of an algorithm that we need to perform on the input signals. In today's example, we'll be skipping this part and we'll try to simply get the output as it is. That is, we'll try to loop back our input signal so that a continuous stream of our own voice is heard over the speaker. In order to do that, I simply need to write the data onto the audio codec. To write the data onto the audio codec, the command is DSK6113 underscore AC23 underscore write, which takes two parameters, the codec handle and the channel information that has to be written. In order to write both the channels, this command will be copied twice, where first the left channel information is written and in the second half the right channel information is written. Once we are done with this, the while loop completes, because if we now read this while loop is now working in a pooling mechanism, because we wait until a sample has been read from the codec. We perform some sort of signal processing. Once the relevant signal processing has been completed, the answer is written onto the audio codec, and the writing of this answer again follows the pooling mechanism, because our processor remains busy until a relevant signal has been transmitted onto the output line. Once we're done with this while one loop, we just need to close the codec, which is done through the close codec command, where we pass the H codec or the codec handler. This completes our code, and we can see from here that the code has successfully built, which means that an out file, audiolab.out, has successfully been generated. All we need to do from here on is to debug the code and try to run it on the DSP kit in such a manner that we somehow hear our own sound, which we'll try to give as input to the DSP kit. The setup on DSP kit has now been changed in such manner that the mic in has been connected to an microphone line, so that we can get our audio, and the output line from the headphone has been connected to the speaker in similar fashion as the last lab, through an auxiliary cable. We can see the connections here. The mic in has been used for the input line, and the headphone has been used for as an output line. Now, as soon as I'll press the resume button on the CCS debug window, I'll start hearing my voice from the speaker as well. I have successfully started the program. Now you may be hearing my voice from the speaker as well. This is a test program. This demonstrates that we are successfully able to loop back our audio from the mic in towards the headphone using DSP6713. Now we can perform any kind of signal processing in between. Demonstration, we come to the end of today's lab. In today's lab, we learned how we can handle analog data using DSPKit. For that matter, the two tasks completed today were sine tone generation and hearing that on audio output line, and second is the loopback of our own real-time signal.